All right, today we are talking about exponential functions, and we're specifically talking about growth and decay functions. If we look at our unit plan here for exponential and logarithmic functions, okay, we're in the middle of working with exponentials. Basically, what an exponential function is any function that has an exponent in our, or a variable in our exponent. So it could look like that. It could look like maybe something times a base with an exponent. It could be more complicated. Maybe it's something like this where we have the exponent having some operations with it. But basically, we're going to evaluate or explore a variety of these exponential function types. The one we're working on today is growth and decay. So these can be modeled to or used to model a variety of situations we'll see in our example problems. But here's where we should start our notes. We should get down these two formulas. The first one being the growth function, that second one being the decay function. And you'll notice that the only difference in there is that with growth, we are adding an R, and with decay, we are subtracting that R. So if we want to interpret what all of these values mean, okay, A is going to be our initial amount. We're going to start with an initial amount, and then we're either going to grow or we're going to decay. Then R is going to be that growth rate. We'll see in our word problems what that means, but it's going to be important here to always convert that to a decimal. We're usually going to get it in percent, and we want to convert that to a decimal. Then X, sometimes we'll use T as well. That's going to be the number of time intervals that we do. So how many times are we multiplying in a row? So we're just going to jump right into examples here because I think it's the best way to learn this. Example 1 deals with growth. A particular bank account provides you with an annual interest rate of 4%. If you invest $1,000 in the account, how much money will you have after 12 years? So we're going to write a formula to best represent this scenario. If we just take my growth rate formula to begin with, okay, f of x equals a times 1 plus r to the x power, then we just want to start swapping out things that we know. So we know that a is equal to 1,000. And we know that r is equal to 4%. But let's think back to that slide there. We're going to want to convert that to a decimal, right? So if we take 4% and divide by 100, that will get us to our decimal. We'll have 0.04. So our rate there is, our R there is 0.04. What we can do is just plug these two values into that formula up top, and the function that represents our equation or our scenario here is f of x equals 1,000 times 1.04 to the x power, because that 1 plus r gives us that 1.04. 1 plus r, 1.04. Okay, and then if we're answering the question, how much money will you have after 12 years? All we got to do is swap in 12 with x in our equation. Okay, we're going to write out f of 12 in this case, because that's the number of time intervals we're hitting. So 1,000 times 1.04 to the 12th power. And if we run through and run that calculation in our calculator, 1,000 times 1.04 to the 12th, okay, we get 1601. And this is going to be in dollars, 1601 and 03 cents. So let's move on and let's explore an example for a decay scenario. So in this case, we purchased a new car for $35,000. Each year it depreciates, loses value at a rate of 5%. what will its approximate value be at the end of the 4th year? So let's first start by writing a formula to represent the scenario. We're going to use that decay formula here, so I'm going to rewrite that real quick just to make sure I'm pulling the right information. This time it's 1 minus r. Oh, and let me rewrite that so it's nice and neat. Okay, and A in this case is equal to that initial value of 35,000. And R is that 5%, but I'm going to convert it from 5% into a decimal, so that is 0.05. And so if I take 1 minus R, that will be 0.95. So my function should be function of x equals 35,000. I'm going to leave that comma in there just to make sure that it's nice and clean to see, times 0.95 raised to the x power. Okay, and now I can answer the question here. So what is the approximate value at the end of the 4th year? So I'm going to take my function, but I'm going to evaluate it for the input of 4. So f of 4 equals 35,000 times 0.95 to the 4th power. And if we plug that into our calculator or into Desmos, 35,000 times 0.55 to the 4th power, we will get, and this is again in dollars, 28,507.72 cents. So let's build up a couple of other examples here. This time I'm going to kind of remove that scaffolding where, hey, we don't necessarily need to build that formula right away if we can plug things in from the start and just answer the question. Example 3 is zombie infection in Hillside High School grows by 15% per hour. The initial group of zombies was a group of 4 freshmen. How many zombies are there after 6 hours? So this is another growth problem. So I'm going to start just by writing out my growth formula. F of x equals a times 1 minus r to the x. Oh, and this is growth, so it should be plus r. I already made a mistake there. Then we know that a is 4 because I have 4 freshmen, so I'm going to start rewriting my equation. F of x equals 4 times something to the x power. I'll leave that blank for now. And we know that our rate is 15% per hour. So R is equal to 15%. And if I convert that into a decimal, it's 0.15. And so my thing that the 1 plus R should be 1.15 to the X. And now I know that, hey, I'm looking at it after 6 hours. That's what my F value represents. So F of 6 is equal to 4 times 1.15 to the 6th power. And if I evaluate that in my calculator or on Desmos, I should get 9.25. But since we're talking about zombies, talking about the number of people, we should actually probably just leave this at 9 because we're not going to have a quarter of a zombie. We're going to have whole numbers of zombies. So 9 zombies should be our answer there. All right, last one here. If we are looking at another growth example, and this one is very popular, talking about investments and savings. Ryan is saving for his college tuition. He has $2,550 in his savings account. It pays 6.25% annual interest. How much money does he have after 10 years? Let's use our growth formula. F of x equals that initial amount times 1 plus r to the x. we can start swapping stuff out. We know initial is 2550, so let's start writing that in. F of x equals 2550 times 1 plus something to the x power. Okay, our rate, 6.25%, let's convert that to a decimal. It's going to start getting a little messy with these decimals in our percentage, but we'll divide by 100. We should get 0.0625. So now that number at the base of our exponent is pretty odd. It's 1.0625. And let me erase that exponent I wrote in there, make it nice and clean above our base. Okay, and once we have that set up, we can just plug in the input, the time intervals that have hit. And this one is 10 years. So if we go F of 10 equals 2550 times 1.0625 to the 10th power. Okay, and that should be a 0 there. Okay, and then we'll get a final number here that will be in dollars. And let's run that, 2550 times 1.0625 to the 10th. We get $4,675.52.